So thank you for coming along to episode 36 of the Innovation Process book. In this episode, we are still on chapter 19, which is a very meaty chapter where we talk about each of the workshops as part of the phases and tools for lean product development. And again, chapter 19 is part of part 4, which is a discussion of the hybrid lean new product development process. Today we'll be covering pages 260 to 268. If you'd like to get a copy of the Innovation Process book, I recommend the paperback because as you can see, there are lots of figures and charts. So grab that QR code underneath the image of the book to get your Amazon copy. We're also offering a course starting October 15th, 2025 on Wednesdays at 3 p.m. Arizona time, which is 5 p.m. and 4 p.m. Central Time, depending whether it's on daylight time or a standard time. So sorry about the confusion there. But grab that QR code that says register now and you can join the course. In 6 weeks, we're going to cover and customize your process to match what your culture, your management team, your product development teams need, as well as the pace of delivery. So we will cover in week 1, waterfall processes, in week 2, agile processes, weeks 3 and 4, we will cover the hybrid wagile process, which is part 3. So check out some prior episodes on that. And part 4, lean new product development. So let's go ahead and jump in to part 4, chapter 19, workshop. Workshop 3, Prototype and Engineering. As the new product development project advances through time, the team learns more information about the markets, technologies, and product. Major project milestones were previously established during the planning and risk mitigation workshop. A key deliverable in any new product development project is to test and learn from customers while creating the technical knowledge to manufacture, distribute, and sell the product. Thus, the prototype and engineering workshop in lean new product development parallels the money gate of a traditional waterfall process. At this point, the business case for the new product is expected to be stable. Product and engineering specifications are agreed upon and implemented. Risk management shifts from identifying potential risks to targeted mitigation of issues that impact the timing, production, or quality of the new product. Commitment to build a specific product of a certain design is established at the conclusion of prototype and manufacturing pilot tests. The new product is moving from a concept to a reality, and the organization transitions from exploration to exploiting their operational excellence in manufacturing. Suggested inputs and outputs for the prototype and engineering workshop are shown in figure 19-12, noting that sometimes iteration is necessary to finalize product and engineering specifications. Participants. With the goal of demonstrating technical readiness for the new product, the workshop or series of workshops may involve different people than previous workshops in lean new product development. For example, design and supply chain are involved along with QA and QC personnel to advance commercialization of the new product. In addition to form and function reviews of the product, other design components often require collaborative decisions. For instance, how the product is packaged is not solely a marketing decision and often involves technical team members to design a carton or a box so that the product can be shipped and handled without damage. Supply chain and purchasing are involved to ensure that raw materials as well as manufacturing equipment are identified before manufacturing ramp up. Likewise, the final product design is reviewed for component, form, function, and integrated operation. An example agenda from a prototype and engineering workshop is shown here in figure 19-13. At this point in the development cycle, manufacturability becomes an important question. The participants in the workshop will focus more heavily on production as well as how to promote the new product in the marketplace. Finance can provide updated business case data based on customer testing with final prototypes and engineering requirements. Manufacturing, supply chain, and quality risks dominate the go-forward planning for the new product project. Tools for prototype and engineering. While the risk matrix developed in Workshop 2 dealt with the product and the new product development project, risk continues to dominate the conversation in Workshop 3. However, the focus of risk management shifts to managing schedule milestones and manufacturability of the new product. Operational risk uses tools from Figure 19-1 in another episode, but prototype planning, as in Figure 14-13, also in another episode, is useful at this stage. Trade-off assessments. One of the important roles played by the chief engineers to make trade-off decisions. A fully loaded product with every possible feature would likely please every possible consumer on Earth. But such a product is completely unfeasible from both a cost and constructability perspective. Even with the typical number of identified features for a new product, there are trade-offs in the level and quality of those components. A simplified Kano diagram can help the team assess which features are table stakes and which are differentiating for the new product. An example of a Kano diagram is shown in Figure 19-14. For a detailed discussion with examples to determine market needs using a full QFD, quality function deployment, and Kano model, please see Product Design and Development Tools written by Carlos Rodriguez. In the Lean Product Development Workshop, we recommend using the diverse team to identify the most important features for the new product using sticky notes on a simplified Kano diagram. In combination with the chief engineer and the knowledge of production cost brought by finance or cost accounting, trade-offs and priorities for the new product features can be easily resolved during the session. Product features are categorized in a Kano diagram on two factors. The first is whether the feature or function is a satisfier that adds value for the customer. If such a feature is absent, would it cause dissatisfaction for the consumer? The second factor for categorization is the focus on the trade-off decision. Is the feature absent or completely fulfilled? Features that are must-haves are considered dissatisfiers if not present. For instance, a hotel room must provide a place to sleep, and if a bed is not present, most customers would be extremely dissatisfied. At the opposite end of the spectrum, unexpected features that completely fulfill the needs of an end user, especially unarticulated needs, are considered delighters. Adding more of these features, as shown in the upper right-hand corner of Figure 19-14, increases the value that a customer assesses for that product. For example, offering free oil changes to a customer who purchased a new car is a delighter and a differentiating factor from one seller to another. In the middle of the Kano diagram are features that increase satisfaction on a linear basis. These are considered performance features, meaning the requests and needs of a customer. Things such as comfort and convenience are performance features. An example of a linear performance feature is computer processing speed. A faster computer offers more satisfaction to a user. Unless the user is an uber gamer, increasing the speed beyond that offered by competitive laptops does not create additional satisfaction. During Workshop 3, the team will determine the must-have features for the product, typically based on work that has already been completed in earlier workshops or prior to the session. Discussion and cost trade-offs are critical to move forward with the final product design and engineering specifications. Participants collaborate in the prototype and engineering workshop to begin to optimize the product and manufacturing process. Decision trees. Another useful risk management tool is the decision tree. A decision tree indicates a starting point and branches to several options. Each branch can further split to additional options and so on, which gives the diagram a tree-like visual representation. Each option or branch is assigned a dollar amount, which can either be revenue or cost. Nodes indicate the percentage likelihood of each branch occurring. Decisions are made to enact the highest value branch. An example of a decision tree in new product development is the expected monetary value. In this specific example, different features, markets, or technologies are indicated on the branches. The full value of the new product is estimated by summing all the different options multiplied by the appropriate percentage. An expected monetary value is a risk-adjusted revenue estimate for a new product. Focus groups. A focus group is a group interview technique led by a trained moderator using collaboration to collect data and information regarding the new product. To evaluate new product prototypes, focus group participants are usually screened to indicate a match with the target market segment and involve 6 to 10 people in each group discussion. Focus groups are held in specialized facilities so that the new product development team can observe the interactions of potential customers with the product or product concept. Recordings and transcripts of the focus group provide valuable data and information for evaluation. The primary goal of a focus group is to learn how potential customers think and feel about a product or proposed product solution. A key benefit of focus groups is the collaboration among participants. In some instances, a subset of the general focus group is used to solidify decisions regarding manufacturing conditions. Internal focus groups assemble subject matter experts, or SMEs, to evaluate process hazards and potential for operating errors. As in an external customer-facing focus group, collaboration among individuals with varying experiences and backgrounds leads to the collection of richer information. In contrast to external product focus groups, an internal process focus group leads to decisions regarding equipment arrangement, raw material supply, product distribution, and other production and sales elements. Failure mode analysis. One of the most popular quality management tools in Lean Six Sigma is failure mode and effects analysis, FMEA, sometimes called FEMA. Like QFD, FMEA is a very sophisticated technique that often requires specially trained facilitators and implementation teams. Discussions readily go astray, deciding whether a potential event is a failure due to causation or is an effect of the failure. Confusion also erupts in determining whether the remedy to a failure is to detect or prevent the error. To work in the spirit of lean for new product development projects, a simplified approach to FMEA is the failure mode analysis. Failure mode analysis can build on or substitute for the quantitative risk assessment. However, in Workshop 2, the risk matrix was developed with a concentration on the product and features. In Workshop 3, the aim is to understand defects that occur in manufacturing the product or mistakes that occur in delivering the product to consumers. Note that FMEA and the simplified failure mode analysis can also address misuse of the product by customers. The intent of a failure mode analysis exercise is to uncover safety hazards and quality defects. Figure 19-15 shows a template for simplified failure mode analysis. As in a qualitative and quantitative risk assessment series, the issues with the highest calculated numbers are considered priorities by the Lean product development team. In the figure, S represents severity of the failure, O represents the occurrence or probability of the failure, and D indicates that the probability that the failure can be detected. The factors of severity and detection balance to some extent risks that might occur in the design and use of the product. Function map. Lean new product development seeks to reduce waste and deliver value. Product waste includes features that do not add value for the customer or the producer. These features might be ones that are added at an expense to the producer, but customers don't need, or they are features that are not included yet and are highly desired by customers, lost revenue. Chief engineers guide the process to manage the trade-off of features and costs early in Lean product development. However, as customers test prototype products and engineering begins designing the manufacturing process, the team must take a hard look at what functions are necessary, cost-effective, and deliver customer value. A product function map is a tool that helps the Lean product development team and subject matter experts, SMEs, evaluate essential features for the new product. While the function map is a complement to QFD and feature prioritization, it is when the team locks down specifications that new product attributes move from nice to haves to must haves. Every must have feature requires manufacturing expenses ranging from supply chain logistics to operations to quality and marketing. Typically, fewer parts and components in a physical product are translated to lower manufacturing costs. In turn, higher revenues and profits can result. A function map is a hierarchical diagram showing the primary purpose of the new product. Primary functions of a product are identified as those that are desired by customers and for which they are willing to pay. Secondary functions are designed during the new product development process, but do not necessarily excite customers or are even seen by customers. You will note the similarity between primary and secondary features and functions with the ideas of value add and not value add regarding necessary business functions discussed previously when we compared procurement to regulatory compliance. An example product function map is shown generically in figure 19-16, where the product and specific function descriptions have been intentionally simplified. The key customer request for the product is to operate smoothly. Breaking down specific features and technical functions, the function map demonstrates a hierarchy. At the highest level, for example, maintain force and absorb gear misalignment were indicated. The function to maintain force was further subdivided to minimize gear friction, minimize distortion, and minimize overall friction. In examining the function map, the team decided that absorbing gear misalignment and cutting edge rotation were functions that did not add value for the customer, the firm, or both. Similarly, functions A and B can be combined to simplify the manufacturing process. The lean product development team would continue to discuss each feature and each function following the hierarchy along with customer needs and engineering specifications to reduce and eliminate unnecessary design criteria. Of course, combining the function map with other techniques in the lean product development tool set can drive better product and process design. Simple designs that are easy to use are desired most by customers. Likewise, simple processes with fewer steps and handoffs operate with higher quality outcomes in a manufacturing facility. Next time, we will discuss workshop 4, which is the process and product optimization workshop. Again, we're in chapter 19, phases and tools in lean product development of the innovation process book. Scan that QR code to get your copy at Amazon, and then scan the other QR code to join the class starting October 15th, 2025. I'd love to discuss this in more detail with you in the virtual class. We meet for an hour and a half each week for 6 weeks and cover, again, waterfall, agile, and both hybrid processes that are familiar to you, and we customize those for your company. Thanks, and we'll see you next time.